So we're back for a little bit more difficult section on equilibrium calculations. And in these type of problems, you might be given enough information to calculate an equilibrium constant, or given an equilibrium constant and other information, be able to calculate concentrations. So let's dive in. The first and simplest kind of problem are calculating the equilibrium constant when you know what the equilibrium concentrations are. So I like these kind of problems because they're easy. And I can see in this problem of nitrogen and hydrogen turning into ammonia, the famous Haber process, they've told me at equilibrium the partial pressures of the reactants as well as the partial pressure of the equilibrium ammonia. So all of these amounts are calculated for you, and we're just going to write an expression and plug in the numbers. Notice that this is a Kp. When all of the reactants and products are gases, you can substitute a little p instead of a c or an eq, but the process is the same. This means partial pressure of ammonia. I square it because there's a 2 in the balanced equation, and there's my partial pressure of ammonia that I'll be plugging in. Same for partial pressure of nitrogen and partial pressure of hydrogen. So it's written essentially the same as an equilibrium constant. Very quickly, here is the atmospheric partial pressures of each of the 3 reactants and products. There is my Kp. So it doesn't get any easier than that. We like these kind of problems. Now what I'm going to introduce is a problem that is also in your sample exercises. It's the next one in the sequence. But this one is going to be slightly more difficult and will involve using a concept called the ice chart. And this is something we'll be using all the time. So I have hydrogen and iodine yield hydrogen iodide, and there's a mistake because it's not solid, it's a gas. So go ahead and fix that. I think the problem is okay in the textbook. This time, all we know is that we have a closed system. That's how equilibrium systems have to be, closed to the outside surroundings. And we have initial concentrations. So they tell us the molarity of the hydrogen and the molarity of the iodine. The only reason why temperature is specified is that you should now have incorporated the concept that temperature impacts the equilibrium position. It has no part in the calculations that we need to do now because we're going to keep the temperature constant. So we know initially what we have. And we know at the end the concentration of the product, hydrogen iodide, that's being made, that's also given to you. So to calculate an equilibrium constant at a specified temperature, I have to know the equilibrium concentrations of all of the reactants as well as the product. So what we're going to create is something called an ice chart. Now I'm going to zip ahead here so I can show you where the work comes from, but I like to do this. I like to write the balanced equation at the top of the ice chart. And so I'm going to go ahead and write again that it's hydrogen plus iodine. And I'm just going to assume those are gaseous, so I'm going to get lazy here and not write that in. Yields 2 hydrogen iodide. Now let's look at the information they gave me. I call this an ice chart. Very important concept to grasp because you'll be using this in much higher level problems as the year goes on in the spring. Where does the name come from? Initial concentrations, change in concentration, equilibrium, ICE. That's where the name ice comes from. Our textbook orients the ice chart in this fashion. We'll occasionally be using the Zumdahl textbook, which orients it in more of a, instead of a vertical system, it lines them up horizontally. But the bottom line is the values written on this first row represent the starting concentrations. They will undergo some kind of change, which might either be subtracting from the original amount or adding to the original amount. And at the end, you get the 3 concentrations that you need to be able to plug into the equilibrium expression. So if you wanted to earn some easy points on an AP Chemistry exam, at the very least, you could start by writing the equilibrium expression, which of course is going to be hydrogen iodide squared divided by the concentrations of hydrogen times iodine. Now you notice that they get kind of sloppy. Since these are all really gases, they could have put partial pressures in there. That is a primitive too. So they could have put partial pressures in, but instead they gave us the concentrations and molarities, and that's okay. Squared here because of the 2 in the expression or in the equation. So when I know what I'm being asked for is to calculate an equilibrium constant, at least I get a point or half a point for setting up what I've got and where I need to go. Now let's look at where the numbers come from. You have to pretend on the initial line that the hydrogen and the iodine haven't touched each other yet. So if they haven't bumped into each other, we got no hydrogen iodide initially. Now as these two bump into each other in this gaseous container, they're going to get consumed. That's why there's a negative sign, because they combine together to make the hydrogen iodide. Now here is where stoichiometry kicks in. They told us in the problem, this was given, that there are 1.87 times 10 to the negative 3 molar concentration of hydrogen iodide. So its change is pretty easy to calculate. If you start at 0 and you end with 1.87 times 10 to the minus 3, then you had a net increase in concentration of that amount. Whatever this one increases by, these two guys are going to decrease by a proportional amount, and now there's the stoichiometry. You can look at this as two ways. You could say for every mole of hydrogen or iodine, I make twice as many moles as hydrogen iodide. Or the other way to think of it is, whatever amount of hydrogen iodide I made, I must have started with half the amount of hydrogen and iodine. So that's where these numbers here came from. If we know that the hydrogen iodide increased by 1.87 times 10 to the minus 3 molar, then each of these two substances had to decrease by half of that amount. So this number divided in 2 are these two numbers. And they're negative numbers here because the initial amount loses this amount to give you the equilibrium amount. So in this particular case, we've put it together in tabular form to create all of the values that I need. I'll be putting this number here, these two numbers in their appropriate spot here, and then I always double check the equation to make sure I have no coefficients, or if I do, to square or cube as necessary. That's called an ice chart. It's your first time seeing it. Make sure you understand the concepts behind it. We're going to ratchet that level of difficulty up a little bit more. So as we get into the problem then, written in much neater form than my crappy little pen here, we can see that they've written the expression, they have punched in the numbers, they have calculated the KQ, which by the way, or KC, you can tell I'm kind of old school. You can see that that's a big number, greater than 1, and that means that at equilibrium, products will be favored. Let's try one or two more. By the way, this was sample exercise 15.9 in the textbook. They had some pre-made PowerPoint slides, so I used those, but it's the same calculation and the same final answer. Notice that the same method could have been applied to a gaseous equilibrium problem if you were calculating Kp. The only thing you'd substitute in here would be partial pressures instead of molarity. Let's go up one or two more levels of difficulty. Now, when you are calculating equilibrium concentrations, you need to be able to look at what's been given to you and what do you need to know. So if I look at this problem, they give me a balanced equation. They give me an equilibrium constant. Again, they only specify the temperature because equilibrium is dependent upon temperature. And they tell you at equilibrium that you have this many atmospheres of hydrogen, that many atmospheres of nitrogen, but we don't know what the partial pressure is of ammonia when it's at equilibrium. Notice that this one's a little bit simpler. You didn't necessarily need to do an ice chart, but you need to do this. Every time they give you one of these, you write the equilibrium expression, and this time we've written it as a Kp because they're all gases, and the information was provided in partial pressures and atmospheres. So they've written the expression, making sure to square the ammonia concentration and to cube the hydrogen concentration. Well, the thing I don't know, and that's often X, is what's the ammonia concentration. So that's where this X squared comes from. I was given the partial pressure of the nitrogen. I was given the partial pressure of the hydrogen. On these types of problems, the most common mistake is math. You forget to cube or square something. You get an answer that's X squared, and then maybe you forget to take the square root. So at this point in time, it's simple math. And you can then solve for X after putting in the given equilibrium partial pressures to get the partial pressure of the ammonia, which is what the problem asks for. If you have time and you want to check, you can always substitute in the partial pressure of the ammonia, punch in the other two numbers that were given, and make sure that the Kp that you get matches the one that was supplied to you in the problem. And that, by the way, was over here on the far right hand side. So that one doesn't really need a nice chart. It was a pretty straightforward one. Let's move on and try one more level before I call it a night here. Okay, this one is interesting because now they've done something kind of mean to you, which you have to be watching for. Oh, no, this one isn't the mean one yet. It's still a 1 liter flask, so they haven't changed the volume. And if I give you 1 mole of hydrogen in a flask and 2 moles of hydrogen in a flask, right off the bat, I know the molarity. 1 divided by 1 is 1 molar hydrogen and 2 molar in iodine. They give you the value of the equilibrium constant. It's right there, 50.5. Looks familiar. And now this time, they want you to find the equilibrium concentrations of all 3 of those substances, the product as well as the reactant. What I like to do, as you can see here, is to write, sorry about that, he's a little sensitive. I like to write the equation above my ice chart. And the initial concentrations were easy to do because we're in a 1 molar flask. And I've got 1 molar in hydrogen, 1 molar in iodine. We pretend they haven't bumped into each other. We got nothing as far as hydrogen goes. Now the chart gets a little different. And what gets different is we kick in what my 8th grade algebra teacher, Mr. Tuttle, said, we kick in an X. So if we're in a 1 to 1 to 2 ratio, and you know these two, the reactants, are being consumed to make some hydrogen iodide, whatever amount you lose in hydrogen has to be the same as the iodine because they're in a 1 to 1 ratio. And they're losing or decreasing in concentration because they're getting consumed as they produce some hydrogen iodide. How much hydrogen iodide? Twice as much as whatever they lost there. So this is where we let X stand for the change in hydrogen and iodide decrease, and 2X represents the increase in concentration of hydrogen iodide product. So what you do is you simply subtract, and we have 1 minus X molarity in hydrogen, 2 minus X molarity in iodine, and 2X is the molarity of the hydrogen iodide. There's good news and bad news. Well, mostly it's all good news here. So now, when you put those numbers in and set them equal to the given equilibrium constant, you get a quadratic equation looking kind of thing. you got all these x squareds and something x, and then you got the standalone number here, which you could, using algebra, rearrange into a quadratic expression, and which you would punch into your calculator. And now let me give you the good news on that. They're not going to make you use quadratic equations anymore. That's one of the major changes on the test. So you probably won't see a problem like this, but I need you to be aware of the concept of the stoichiometry. If hydrogen and iodine are losing X in concentration, then hydrogen iodide must be increasing in concentration by 2X. Now, we're not going to use the quadratic equation here, but they did in the sample exercise problem. And when you end up with an answer, let me back up on that one just to be sure. When you end up with an answer where you solve for X, you know that when you do the quadratic equation, you have two possible answers, and one works and one doesn't work. If you use one of these numbers, like the 2.323, you get negative concentrations of hydrogen and iodine, and that's just simply not possible. You can't have less than 0 concentrations of substances. So the answer is X equals 0.935. That's what X is equal to. That's the hydrogen and iodine. Therefore, 2X must be the concentration at equilibrium of the hydrogen iodide. So good news, no equilibrium expressions that involve the quadratic equation this year. Leastways, that's what they told me. So if you can hold on to that thought, the last little mini section of this equilibrium PowerPoint is going to have to do with something called the Q, or reaction quotient, and I'm going to stop there.